Hey guys, it's Angela Swilly, and today we're going to be talking about 8.9 Henderson-Hasselbalch equation. And you need to be able to identify the pH of a buffer solution based on the identity and concentrations of the conjugate acid-base pair used to create the buffer. All right, so calculating the pH of a buffer. So first of all, last lesson, 8.8, was the conceptual idea or the concept behind this, without using a lot of numbers necessarily. And then this lesson is how to quantitatively use the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation, which you've seen before, is pH equals pKa plus log of the base and log of the acid. Now, not a log of the concentration of the base over the concentration of the acid. So sorry. So this down here, remember, is going to represent our reactants. So it means we're starting with an acid. So we will be using the Ka, and so we can get the negative log of that. Just so you know, I don't know if it makes a difference to you, but this would be the conjugate base. So a lot of times when we've been writing it, we'll say Ha for the acid, and we'll say A minus for the conjugate base. And we're going to talk, I'm going to show you again in a little bit, but you've already seen this. But we'll be using the POH equals the pKb plus log of concentration. So I'll show you that in just a minute as well. And when we prepare a buffer, usually the concentration of the acid equals the concentration of the conjugate base. And so normally, when we prepare a buffer, well, if the concentration, so if this is, 1 over 1, that's going to equal 1, and we cross that out because the log of 1 is 0. And so pH equals pKa plus 0. That is where we get our pH equals pKa from. Remember that this is true at the half point equivalence, or it's also called the midpoint. So when you're calculating the pH of a buffer, if the concentration of the acid is greater than the concentration of the conjugate base, then pH is going to be less than pKa. That means you're closer to the starting point, because as you move further, they're going to end up being equal. And then the pH will be greater than the pK at another point. So if your conjugate base, once it becomes greater than your acid, then the pH is greater than the pKa. And if you ever get to the point where your acid is much greater than your conjugate base, or your conjugate base is much greater than your acid, then it actually then loses the ability to function as a buffer. Now remember, this is only showing a part of the titration curve. Here's the equivalence point, so it's probably going up more like this. And remember that this blue square is kind of showing you the buffering region. But normally, even a lot of times you'll even see it like right in here, even tighter. And it can be, that whole thing is the buffering region, but when you guys have seen it, we've been placing points, it's a little bit tighter in there. But that entire region, or that entire blue square, can be called the buffering region. And this usually corresponds with a tenfold difference, meaning the buffering region is effectively pKa plus or minus 1. All right, so let's look at example 1. Now, example 1, what is the pH of a buffer that is 0.12 molar in lactic acid and 0.10 molar in sodium lactate? So if you'll notice, your lactic acid is your acid, your sodium lactate is going to be your conjugate base. And it gives us the lactic acid Ka, and so it wants us to find the pH. So if we're going to use the Henderson-Hasselbalch, we need the pKa. And to do that, the pKa is the negative log of Ka. And when you calculate that out, you get 3.85. So then we can plug this into our Henderson-Hasselbalch equation. and it's 3.85 plus the log. Our concentration of our conjugate base was 0.10, and our concentration of our starting acid or our acid is 0.12. And so once you calculate this, you get a pH of 3.77. Now, if you're calculating the pH of a weak base, then you have the POH equals pKb plus the log of the acid, which is the conjugate acid, okay? So this is what we've been putting is for the base. A lot of times you'll see me put B, and then this is the conjugate acid. Oh, I'm going to put a G instead of a J. And a lot of times we write it as concentration of AHB plus to show it as the conjugate acid. Now, I want to tell you this. If you put this B right here, the concentration of the base, on top and the conjugate acid on the bottom, you can use the other equation. So let me show you. Like, because you're just going to have to, they have this equation, I believe, on the equation sheet. We need to look. I don't have mine. Actually, I have it right here. Let me look. Yeah, on your equation sheet, they give you the pH instead of the POH. They give you that one. They don't give you both of them. And so if you did, I'm just trying to help you not have to like memorize. But this isn't hard to memorize because it's opposite kind of the other one. But basically, you would just say the log of the base over the log of the HB plus or the conjugate acid. And if they gave you the pKb, because if you start with the base, normally they will, you could just do your, as long as they haven't said it's at a weird temperature, you could just do your K, KW equals Ka times Kb to figure out what your pKa would be. Okay. So again, you can use the POH one, not a problem. I actually like to use that. It's just, it's not given to you on your equation sheet. So if you want to, not have to try to think about memorizing it, then this is a good alternative. But if you do use the one in the blue box, the POH, then once you find the POH, you just subtract it from 14 to then convert it to the pH like we've been doing. All right, so example 2. If you want to try to do this on your own, you can pause the video and then resume to check your answer. All right, so the first thing we're going to do, if you're ever starting with a base and going to your conjugate acid, they're going to give you the Kb. And even when you reverse these equations, you're still going to be using what the original forward reaction was. So we need to find our pKb. And so to do that, we're going to take the negative log of our Kb. And it tells you it's here at 25 degrees Celsius, which most of them are going to be. And so when you do that, you're going to get a pKb of 3.268. So now, to find our POH, we're going to take our pKb plus the log of the concentration of our conjugate acid, which is going to be 0.1. And then our base that we started with is also 0.1. So remember, when we do that, that's going to cancel this out because it's going to cause this to be 0. So our POH equals our pKa. Not pKa, pKb. And then to find the pH, we need to subtract it from 14. And to get that, when we calculate that, we get 10.732 as our pH. All right, there's going to be several problems here with this one, but if you want to pause them at the different points and try to solve it on your own and then resume, please feel free to do so. All right, so it gives us that it tells us we have one solution of buffer and that it's made up of acetic acid and then sodium acetate. And we've got 0.1 moles of both of them. Their molarity's the same. So they want to find the starting pH. So first of all, we need the pKa. Again, that is the negative log of the Ka. So that is going to be 2.745. Okay. And then we take our pH equals pKa, 2.745, plus the log of we need to do our conjugate base first, 0.1 over 0.1. So again, when we have the exact same concentration, that's going to put this as 0. So our pH equals our pKa. That means we're at the halfway equivalence point, or halfway point to the equivalence, or the endpoint, however you want to say it. And our pH is 2.745. Now, what if you add a little bit of acid to this? It wants us to find out what's going to happen to the pH then. Well, we have to have our concentrations, and our concentrations are going to change just slightly when we add something to it. So now, if you'll notice, when we're adding an acid, remember it reacts with the conjugate base. So that's why this equation has reversed, but you always use everything in regards to the forward reaction. So we can still use Ka and all of that kind of stuff. So if you'll notice, our limiting reactant is our acid. So the 0.01 moles that we add to it is going to go away because it's going to completely react with the conjugate base the conjugate base that we have. So that means that we're going to have a change of minus 0.01 to the conjugate base it's reacting with, and plus 0.01 for the acetic acid. So at equilibrium, our conjugate base is going to be 0.09. We're going to have none of our hydrogen ions left, and our acid is going to be 0.11. Now remember, these are in moles, not concentration, but our solution is 1 liter, so that's going to be divided by 1 to get our concentration. So I like to always put over here to remind myself the concentration of the acetic acid in this case is 0.11 molar. The concentration of my conjugate base is 0.09 molar. Plug into HH, which means Henderson-Hasselbalch. So if we want to find the pH, we already know our pKa of 2.745 because we're still using the same substances. But now we have 0.09 over 0.11 as far as our concentrations go. And when you plug this into your calculator, you get a pH of 2.658. Which should make sense because at the half point equivalence, we had 2.745. If we add a little bit of acid to it, it's going to change just slightly, not a lot, but slightly. And it's going to decrease since it was, acid was added to it. Now, what happens if you add an OH or add a base to this? If you want to pause and try it on your own and then resume, feel free to do so. All right, so we used the same concentrations as last time because they've given us the same addition of OH negative. And so again, we're going to have this is going to change in minus 0.01 to get 0.09. And we're going to have a plus 0.01 in our products here, and that's going to give us 0.11. And we have none of the hydroxide left over because it completely reacts with the acid that we have present. And so I just like to write over here. Oh, nope. what our concentrations are so I don't get them confused. And then our conjugate base. All right, so we plug it in the Henderson-Hasselbalch to get the pH. The pKa is still the same. We're still using the same acid. And so we have plus the log of 0.11 divided by 0.09. And when you plug this all in, it tells us that our pH is 2.83. So if you remember, when our concentrations were the same of the acid and conjugate base, we had a pH of 2.745. And when we added base, like a very small amount, we went up to 2.83. And when we added acid, the pH went down to 2.658. But this is not a huge change. When you change from like pH of 2 to pH of 3, that's a tenfold change. That's a big change. But this is a very slight change. And it's because it was a buffer solution, so it's able to resist, that drastic pH change. All right, so the I do. Calculate the pH of a buffer solution for a weak acid if the concentration of the weak acid is 0.137 molar and the concentration of A negative, which is the conjugate base, is 0.972 molar. The Ka for this acid is 1.51 times 10 to the negative fifth. If you'd like to try this on your own, pause the video and resume when you're ready to check your answer. All right, so first of all, we need to find the pKa, and again, that's the negative log of the Ka. And we get 4.821. So to find the pH, we say 4.821 plus the log of the conjugate base molarity, 0.972, divided by 0.137, which is the molarity of the acid. And once you calculate those, you get a pH of 5.672. All right, guys, I hope you have a great evening, and I'll see you in class.